So what we're going to look at now is how electrons are shared between atoms and how the sharing can actually produce entire molecules. So let's start off with the basics here. Let's just start off talking about the bonds. Now you can think of bonds as kind of an electron highway. Now in real life, when we draw this or when we picture atoms, we use lines to represent bonds. We might use little springs in between little balls. When we use our model kits, we might use wooden sticks. But we use something to represent electrons zipping back and forth between two atoms. Now, if you were to actually zoom in and look at an atom and another atom sharing electrons, you would basically see, and this isn't a very good picture here, but you would basically see a fuzzy electron cloud overlapping with another fuzzy electron cloud of the neighboring atom. And two electrons would kind of zip back and forth between them. So it's not really a pathway, it's not really a highway necessarily, a straight line or straight path. It's just the electrons spending time in both clouds. But like I said, for now you could think of these bonds as the lines or the sticks or the springs or whatever that you happen to draw or use in your model kits. In any case, each line or each spring that you use or each wooden stick that you use represents two shared electrons. They go back and forth between those two atoms. So every time you see a line, count it as two. Every time you put a spring on a model, count it as two electrons. Every time you have a wooden stick on a model, it counts as two electrons. Now, the nuclei of each atom sharing those electrons are kind of playing tug of war with those electrons. They're being pulled by one atom this way, then they're being pulled by the other atom that way, and sometimes they're pulled evenly because both atoms have nuclei that have even strength. Sometimes one nucleus is stronger than the other and tends to pull the electrons towards it, and the electrons spend more time around this atom than this atom. And we'll talk about whether these electrons are pulled evenly or if there's a big discrepancy, if one's really strong and one's really weak. We'll talk about that later on when we talk about polarity, but we've got a long way to go before we get there. Now, there's three types of bonds that we're going to deal with. The first type of bond is what we call single bond. So basically, it's just one line between our atoms. Now here I have two carbon atoms pictured, and if I draw one line, it represents two electrons. And that's a single bond. And if I have a double bond, it's basically representing four total electrons being shared. And if I have a triple bond, you can imagine there's three lines or three springs, and that's 2, 4, 6 total electrons sharing those, are being shared between those two atoms. So we're going to make single, double, or triple bonds. And no, for those of you wondering, you cannot have 4. That won't work. All right, so let's talk about 3 examples quickly. Now, let's look at hydrogen. Hydrogen only has one valence electron, so hydrogen's not really happy about the whole situation because it needs to fill that first energy level. Remember 1s2? It needs to have 2 electrons in there to be stable. It only has 1. So little hydrogen's going to go look around for another, maybe little hydrogen, who's in the same boat. And the 2 hydrogens look at each other and say, you know what? What if we share our electrons? What if this one and this one? What if they both hang around me for part of the time, and then I'll send it back, and those 2 will hang around you for part of the time? And they'll go back and forth and back and forth and back and forth, and everybody's happy. Then we have what we call a single bond. It's basically 2 electrons being shared between 2 atoms. And again, we represent that with one line or one spring or one stick when you use your model kits. Now let's look at oxygen. Oxygen has 6 valence electrons. And again, if you don't remember how to figure out valence electrons, you can cheat. You can look at your periodic table. The periodic table's group number will tell you the number of valence electrons. So if oxygen's in group 6, you might also know it as group 16. If you see that it's in group 16, just ignore the 1 and then say, oh, it's in group 6, so it must have 6 valence electrons. So those 6 electrons are going to make oxygen unhappy. It's only got 6. It needs a grand total of 8. So it looks at the other oxygen, who just happens to be in the container with this first oxygen, and the 2 oxygens look at each other and say, what should we do? There's nobody here who's going to give us 2 electrons. They would love to see magnesium, because magnesium comes in and right away gives away 2 electrons. but there's no metal like magnesium in a container. There's only a bunch of oxygens. So they both look at each other and they say, what if we cooperate? What if we make a covalent bond? What if we share electrons? So this first oxygen will take its 6 plus 2 more from this oxygen. And those 8 electrons will zip around this oxygen for part of the time. And it's not a permanent thing. They're going to share, which means it goes both ways. So this oxygen is going to take its 6 plus 2 from this oxygen. And they're going to go zipping around over here, and this oxygen's got 8. And because they shared 2 sets of electrons, we represent that with a double bond. And each oxygen is happy. They each have their 8. And this is what a nicer picture looks like. Sorry about those guys. They should be 2 distinct electrons. In any case, that's a double bond. 2 sets of electrons being shared back and forth. Now let's look at nitrogen. Nitrogen's got 5. Again, if we don't know that, we could just look at the periodic table. It's in group 5. If you use the 1 through 18 method to number them, just get rid of the teens. It's just 5. So here's the first nitrogen. We'll call this nitrogen 1 and nitrogen 2. Nitrogen 1 says, I've got 5 of my own, give me 3. And this guy says, no, I have 5, I need 3. So then they hash it out and they say, what if we cooperate? What if we make some covalent bonds? So this guy, he has his 5, and he goes and borrows 3 more. 1, 2, 3 from that guy. And then he has all 8. And this one says, I'm going to take my 5 and 3 of yours. And they'll zip around me, and they'll go back and forth, and you'll have 8, and I'll have 8, and you'll have 8, and I'll have 8. So these 3 sets, 1, 2, 3, is hooked up with 1, 2, and 3. The 1s are hooked up, the 2s are hooked up, and the 3s are hooked up. Now let's draw a nicer picture. We'll do the N and the N. Remember, we've got 1, 2, 3 sets of electrons. So 1, 2, 3 sets of electrons. And then these electrons here are usually drawn on the outside like that. And that's what we call a triple bond. 3 sets of electrons, so 6 electrons total. That's a lot of electrons being shared between 2 little atoms. So let's look at water situation. Oxygens got 6 electrons. Hydrogens only got 1. Now this oxygen here looks at these little hydrogens and says, what if we work out a deal? What if we cooperate? What if we make covalent bonds? What if you take your little electron and give it to me for part of the time? And you take your little electron and give it to me. And I'll have my 6 plus your 1 and your 1, and I'll have all 8. And they zip around me. And then I'll send mine back, one of mine back with you. And you'll have 2, which is what you want, because remember, you only need to fill the 1s2 sublevel. And you'll have 2 over here, because you want to fill the 1s2. So you'll be happy, and I'll be happy, and everybody's happy. So we end up drawing it like this. And we'll talk about why it's bent in a minute. But overall, it looks like that. And to make things more interesting, oxygen is a big, big bully. Oxygen says to poor little hydrogen, remember hydrogen only has 1 proton, very tiny, tiny nucleus compared to oxygens. In any case, oxygen says to hydrogen, I'll share with you, but it's not going to be an even sharing. So hydrogen's going to give up its electron, it's going to hang out around the oxygen most of the time, and poor little hydrogen's not going to have its electron much. But it still plays a sharing game. And we'll talk about this a little bit more later on when we talk about that polarity concept. So just remember, things can share electrons back and forth evenly, or you could have some big bullies and some poor little weaklings, and you can have an uneven sharing. But either way, they're sharing electrons. Now, some definitions here. We're going to use the term unshared pairs of electrons. Now notice what these are pointing to. They're pointing to those and those. These are unshared, meaning they're only on the oxygen. So they're only on the oxygen. The ones in between are what we call our bonding pairs, and we represent those with dashes. So this really should be represented with a dash, this should be represented with a dash, but those separate sets of electrons, unshared pairs, meaning they're not being shared between 2 atoms. Those are going to become important. They have to be included in your drawings, and I'll show you how to do that in a little while, but they are really important in determining the shape, which we'll talk about in a minute. All right, here we go with the shapes of these molecules. Now I'm going to show you how to draw the molecules out and then figure out the shapes, but let's just review the shapes first, and then we'll put it all together in a little while. Now there's something called the VSEPR theory, the valence shell electron pair repulsion theory, which is quite a mouthful. Now, honestly, I really don't care that you can remember this fancy name. I really don't care that you can remember all of these words. All I care about is that you realize that negatives repel negatives. So if you have little electrons right here, here's your atom. We'll color this guy in here. And there's two unshared electrons. Remember, we just talked about unshared pairs of electrons. If there's two electrons, they're negative. And if you have an electron cloud over here for another bonded atom, that's negative because electrons are negative. These guys don't like those guys, so they push each other away. They don't like each other. That's what you got to get out of this. Valence shell, which is your valence electrons, electron pairs. You could have pairs of electrons or you could have electron clouds around atoms. Repulsion, they repel, they don't like each other, theory. So anytime you have negatives, they move so they can stay as far away as possible. That's all you need to know to understand this. Anytime we have negative regions, they try to get as far away as possible. So here we're going to talk about the shapes of the molecules. There are 5 basic shapes that we're going to cover in this class. There are many, many, many other shapes. There's many odd, weird molecules out there that'll fit in those other categories. But these are the 5 basic categories that we're going to use in this class. The first is linear, basically a straight line. The second one is bent, not a straight line. It bends like that, whereas the first one just moves straight across. Now we have 2 that start with trigonal. Trigonal, trigonal. Trigonal kind of makes you think of triangle. So we have an atom here, an atom here, atom here, and atom here, kind of makes a triangle. And so does this guy. Except planar lays on the same plane. And we'll talk about what that means in a little while. And pyramidal kind of sits up like a pyramid. You have 1 on top, and then the 3 down here making the base of the pyramid. Whereas over here, it all lays on the same plane. And finally, number 5, tetra. Tetra means 4. Remember your prefixes. Tetrahedral. And we'll take a look at what this is. The good news is you're always, always, always going to have this image. On every quiz, every test, every lab, every exam that you take, you'll have this picture. And the pictures are nice and dark, so if you don't know how to draw these, you could always lay your paper over this image and you could just trace them. It's in your notes right now, but it also should be in a reference sheet that you're going to get. If you haven't gotten it yet, please ask for it. This is going to become very important, this reference sheet. All right, so here's your basic shapes. Again, linear, bent, trigonal pyramidal, trigonal planar, and tetrahedral. Now let's mark up your paper quickly. Linear versus bent. Now first up, you can have linear as a straight line with 3 atoms. You could have linear with just 2 atoms. Either way, it's in a straight line. Now notice over here, it's bent. This and this are similar. There's 1, 2, 3 atoms. 1, 2, 3 atoms. The only difference is those guys. So on your notes, circle that. Circle those electrons and circle these electrons. That's what makes bent different than linear. If the electrons are there, it's bent. If they're not there, it's linear. We'll talk about why it bends in a little while. Now, here's the trigonal bit. We got trigonal pyramidal and trigonal planar. They both have 1, 2, 3 atoms. Put this on your paper. They both have 3 atoms bonded to the center guy. Over here, 1, 2, 3 atoms bonded to the center guy. The only difference is this set of electrons. Circle that, highlight it, put a big smiley face there. That determines whether or not it's going to be trigonal planar and they all spread out equidistant from each other, or if they all push down. Remember, these negatives repel them and they push them down and it kind of sits up like a pyramid. So you're going to look for those electrons when you have 3 atoms bonded to the center one. If they're there, it's pyramidal. If they're not there, it's planar. And finally, if you have 1, 2, 3, 4, it's tetrahedral. All right, let's go through this fast, and then I'm going to explain a little bit more, and I'll show you some model kits. But this is just an example linear. Now notice we get fancy here. We got a double bond. You could have single bonds, you could have double bonds, but either way, this guy is straight. So hint, hint, if you're asked to make a linear molecule, and you're using your model kits, maybe, if you have 3 atoms involved, maybe you got to use some double bonds. Hint, hint. Now here's our bent molecule. Now notice that these guys are present. those valence electrons are responsible for pushing these little hydrogens down and away from the oxygen atom. And we end up with this bent structure. It's not straight anymore. In the real world, it gets bent like this. And again, we'll talk about where those electrons come from in the first place in a little while. But right now, you just have to know that if they're there, it's not straight anymore. In the real world, it's bent. Now here's one of our trigonals. This is trigonal planar. We're going to do pyramidal in a minute. So here we draw it out on paper, and again, we'll learn how to do this in a little while. But you count. There's 1, 2, 3 atoms bonded to the center guy, and there's no valence electrons on that center atom. That means that 1, 2, 3, they're going to spread out so they're equidistant to each other. There's 120 degrees here, 120 degrees here, and 120 degrees here. How did I get 120? What's 360? A whole circle divided by 3. Isn't it 120? So when you only have 3 regions, 3 electron clouds, remember these are all negative, they all repel each other. When you only have 3, they spread out like this. If you have 1, 2, 3, 1, 2, 3, and, this is the big difference here, and a set of electrons. So technically you have 4 regions of negative electrons that all repel each other. If you have that, then you end up with this pyramid structure, because those electrons up here push these guys all down, and it ends up pushing them down so they make the base of a pyramid. So trigonal pyramidal. What do you look for? These guys. And finally, one of the easiest ones, tetrahedral. Tetra means 4, so if you have 1, 2, 3, 4 atoms bonded to the center guy, in the real world, it wouldn't look like this with 90 degrees between them. They all spread out. Remember, we've got some going up, we've got some coming out at you, we've got some going back here, some going back there. So if we draw this using some 3D arrangements, we're going to end up with this kind of a structure, with this tetrahedral structure. Now let's get a little more in depth with this.